A light switch, starting off. Flick it 7 times, fast, click, click, click. Is the light on now or off? You could trace all 7. Off, on, off, on. Fine, 7 is small, but what if you flick it 100 times? You're not going to trace 100 clicks. There should be a way to just know. There is, and it never touches the number itself. Just one question, odd or even. It answers the switch, and then a lot more. By the end, that same question will prove something impossible. Think about what a flip actually does. It swaps the state. Off goes to on goes to off. So the light doesn't care which flip you're on. All that matters is whether the number of flips is odd or even. Odd number of flips, it's on. Even number, it's off. 7 is odd, so it's on. 100 is even, so it's off. You didn't trace a single click. You just read whether the count was odd or even. That's what we'll call its parity. Now something that looks harder. Add up every number from 1 to 10. Don't go for the total, just watch odd and even. Even plus even is even. Odd plus odd is also even. 2 odds cancel out. Only an odd plus an even makes the sum odd. So a sum is odd only when it holds an odd number of odd pieces. 1 to 10 has 5 odd numbers. 5 is odd, so the sum is odd. It's 55, but you knew it was odd before adding anything. Try 1 to 11. Now there are 6 odd numbers, and 6 is even, so the sum is even. 66. Same quick check, longer list. So why do 2 odds cancel? Every odd number is a pair with 1 left over. Put 2 odds together and you get 2 leftovers, and those make another pair, even. And the odd numbers do something neat. Add them in order and each one builds a bigger square. 1, 4, 9, 16, 25. The sum of the first n odd numbers is exactly n squared. And whether that's odd or even just follows n again, the count of odds. The first 10 odds add to 100 even. The first 11 add to 121, odd. Same rule in square form. Here's that switch on a bigger scale. A row of 100 lockers, all shut. Pass 1 flips every locker. Pass 2 flips every second one. Pass 3 every third. 100 passes in total. Which lockers are open at the end? A locker is open only if it was flipped an odd number of times. And it gets flipped once for each of its divisors. 12 has 6 divisors, which is even, so it ends shut. 9 has 3, 1 and 3 and 9, which is odd, so it stays open. So why are most of them even? Divisors come in pairs, d and n over d. The only numbers with an odd count are the perfect squares, where the middle divisor pairs with itself. So the open lockers are exactly the perfect squares. The same squares we just built from the odds. Let's make it harder. A marker starts on the near bank of a river and crosses back and forth. Each crossing does the same thing a flip did. It swaps the side, near, far, near, far. After an even number of crossings, the marker is back where it started. After an odd number, it's on the far side. Say it crosses 101 times. 101 is odd, so it's on the far bank. The same odd or even that rid the switch now tells you a position after 100 steps. And it doesn't matter how messy the path is. 1,000 crossings, 1,000,000. All that counts is odd or even. 1,000 is even, so it ends right back at the start. Now watch odd and even beat straight calculation. Take 10 and try to split it into 3 groups that are each an odd size. 3, 3, 3 is 9. 3, 3, 5 is 11. 1, 3, 5 is 9 again. It keeps missing 10. And it always will. Odd plus odd plus odd is odd. 2 of them cancel. And the third leaves it odd. So 3 odd groups always add to an odd number, and 10 is even. It's not that it's hard, it's impossible, and odd versus even shows that before you even try. Here's another. Take a checkerboard and remove 2 opposite corners. Can 31 dominoes cover the 62 squares left, each one lying across 2 neighbors? Look at the colors. Opposite corners are the same color, so you took away 2 dark squares. That leaves 30 dark and 32 light. But every domino covers 1 dark and 1 light. so 31 dominoes would need 31 of each. 31 can't be both 30 and 32. It can't be done. The colors don't balance. One more. Put a plus or a minus in front of each number from 1 to 10. Can the result ever be 0? Start with all pluses, that's 55, odd. Now flip one sign, say the 4. That doesn't change the total by 4, it changes it by 8, twice the 4, an even jump. And an even jump never changes odd or even. 55 is odd, and it stays odd no matter which signs you pick. 0 is even. So the answer is no, and you didn't have to try a single combination. It even works as a check in real life. Say a bill has 3 items, 8, 6, and 4. Every price is even, so the bill is even. You pay with an even amount, around 100. Even minus, even is even, so the change has to be even. You didn't subtract anything to know that. The till gives you 85 back. 85 is odd. That's wrong, right away. Odd or even caught a mistake you never had to calculate. Stop and look at what this did. It told you which state a toggle lands in, which side a path ends on, whether something is possible at all, and whether a total is right. 4 different questions, and none of them needed the actual number. Look back at all of them. A switch, a sum, a crossing, a split, a receipt. Underneath, they were the same move. Odd and even only change in fixed ways, and no even-sized change can ever turn odd into even. Something that holds like that has a name, an invariant. You read it instead of chasing the number. Your turn. 3 coins, all heads up. Each move, you flip exactly 2 of them. Any 2. Can you ever get all 3 to tails? Give it a try, then think about odd and even. Pause here. Every move flips 2 coins, so the number of heads goes up or down by 2, or stays put. Always an even step. You start at 3 heads, which is odd, and it stays odd the whole time. All tails means 0 heads, which is even. Odd can't turn into even, so no. Now change one rule. 4 coins this time, all heads, and each move you flip exactly 3. Can you get to all tails now? Flipping 3 changes the number of heads by an odd step, so it's no longer stuck as odd or even. It can go from even to odd and back. Nothing stops all tails now, and 4 moves get there. 4, 1, 2, 3, 0. So odd and even doesn't only rule things out. It also tells you when they're allowed. Next is 1 plus 2 plus 3, all the way up to 100, odd or even. Don't add it up. Pause. Only the odd numbers matter, and from 1 to 100 there are 50 of them. 50 is even, so the sum is even. It's 5050, but the even part was free. Last one, add up all 12 numbers on a clock face. Odd or even? Count, don't add. Pause. 6 of the 12 are odd. 1, 3, 5, 7, 9, 11. 6 is even, so the total is even. It's 78, but again, one look was enough. Same with 1 to 20. 10 odd numbers and 10 is even, so that total is even too. The list changes, the rule doesn't. This idea goes far beyond switches. It settles which puzzles can be solved and which can't. It's how a computer spots a single flipped bit, and it's a standard way to show that something simply can't exist. One look, odd or even, and a whole question can close. So before you start calculating, ask the smaller question first, odd or even. It changes in fixed ways. It never lies, and one look tells you which state, which side, whether it's possible, and whether it's right, all without the number. Read the parity, and the hard part is already done. That's all for this video.